Okay, well, recall that we were looking at the damped-driven oscillator as exemplified by a mass hanging at the end of a spring. And we said if we call its position downward from its equilibrium position where it hang without moving, u, then we can think of u of t, a function of t, is its position in time. Downward being positive displacement, just for convenience in writing the equations, leads to this result. By Newton's second law, mass times acceleration, md squared udt squared, must be the net force applied to the mass. But the net force applied to the mass, just following physics, is the sum of the applied forces, a force from the spring, a force from the damper. An ideal spring, just experimentally, and some springs are designed to be this way, we said, has its force that it pulls back with when you pull it down, proportional, that is a constant multiple of, to the displacement. If you pull it twice as far, it pulls twice as hard, 3 times as far, it pulls 3 times as hard. So the force from the spring is minus k times u for some constant k greater than 0. Negative, so it's a restoring force pulling, when u is positive, it'll pull it in the negative direction, right back towards equilibrium. And then similarly, the damper actually tries to oppose your motion. If you're moving in the positive direction, then a positive multiple of this will push you in the same direction. So we take minus a multiple, minus a negative number times the velocity at which it's moving. And that's the resistance due to a dashpot damper, which is not really modeling friction. Friction would be proportional to the normal force on the thing. If it's friction of sliding on a table, say you put the mass horizontally or something. But it is what's used in things like cantilever beams and so forth to model the damping. And we can add then for that, this additional thing supposed to be attached down here, some big, think of a big flat plate sitting in a big liquid. If the plate moves very slowly up and down in the liquid, then the resistance is approximately proportional to how fast the plate is moving. And so that's sometimes the way they model a dashpot damper for this simple illustration. But we said also, this is a very useful thing for things like bridge beams and so forth, that the steel can act somewhat like a mass spring system and the girders and so forth. And they're more complicated. You get systems of these equations instead of just one. But this is what leads into all that analysis of interconnected things like steel that vibrate. So there's the basic model. And then we said, let's see, another page back here. There it is. So what happens when you solve this equation is that this is equivalently md squared u dt squared plus c du dt plus ku equals 0 with all these constants m, c, and k positive. And this is a second order linear differential equation with constant coefficients, just the kind we've been studying, where and homogeneous so far. So we use the characteristic equation to find the general solution. And when we did, we found this, because these things are positive, we get the following kind of characteristics. If there is no damping, if you just have the mass on the spring by itself, you get this equation. And here it is up here, just the mass without a damper. And you get complex, you actually get two pure imaginary solutions. And we said that the resulting motion turns out to be a sinusoidal one in time. If this is t and this is the displacement u, with u downward again, then it moves in a sine wave. We call that simple harmonic motion. More generally, harmonic motion being a repeating wave. Usually simple harmonic motion is a sinusoidal wave. There was a nice way to show that from our general solution. I don't want to repeat what we did before, but we'll just say that that's the result right there is that here's t on this axis versus u on this axis, and it's just a sine wave. And there's a natural frequency, we said, at which this results, right? If you write the characteristic equation, we said 1 if c equals 0, we get the characteristic equation m R squared plus, we get the equation U double prime plus KU equals 0. And we're recording today's lecture for someone who's gone, so just be aware it's being recorded. Gives us a characteristic equation. Oops. MR squared plus KU equals 0 tells us that R squared plus K over M plus K over M equals 0. Says that R equals plus or minus I square root K over M. And that tells you that the solution is the undamped case C1 cosine square root K over M, we'll call omega T, plus C2 sine omega T, where omega is square root K over M. This is a very interesting thing about mathematical modeling. A mass spring system without any damping will move exactly the same as long as K over M is the same. So if you double the mass and double the spring constant, it moves the same as the original system with the original M and K. If you quadruple the mass and the K. So there's really only one free parameter here. It's omega, it's square root K over M. Determines the motion of the mass. So we say it's a one parameter system instead of three parameters, right? One of them goes away by dividing through, and then the other one, instead of two parameters, one of them goes away by dividing through. Okay, so that was the first simplest problem. And then we said later, I repeat this because it's been a while since we met, that there's a natural frequency then at which it vibrates. It doesn't matter how you push the system initially, its final motion is like this. It's a sine wave with the same angular frequency, square root K over M, regardless of how you push it. You push it hard, you push it slow, you just pull it out and let it go without pushing it at all. It just oscillates at the same frequency. It depends just on the mass and the spring constant. All right, so now that's going to say something very significant later today. So there's some nice examples in there. Then we might also consider an electronic circuit, because electronic circuits turn out to have exactly the same kind of equation. If you just, we'll mention that just in terms of their inductance and capacitance of the things involved. Okay, we're recording today's lecture just to let you know, because students can't be here. All right. The result of this is a wave, right? If you plot, which said T versus U, yet the motion is a wave. And you can use this to model other things also, like for instance, here's a slinky. And if you push it like that, you can create waves in the slinky. And then there's two different kinds of waves. This is not important for you in math class, but for people that are interested in the physics of this, going to go out and apply it, like I used to work in the aerospace industry. You want to understand a few things. If you just jerk the slinky once, one single pulse goes down there. That's not a wave, right? But if you keep moving it up and down in a regular pattern, then you can create a wave that goes on to infinity. These are called longitudinal waves. Transverse waves on this one, because it moves at a right angle to the waves are at a right angle to the position of the spring. Or you can put longitudinal waves where you shake it back and forth like this and create waves. And this kind of analysis can apply to both these things for waves in a medium, such as a slinky or some fluid or something. Okay, so there's that additional part there. Maybe I should just put this video just for fun. I'll just put a real brief part of this. Okay, so that's all I wanted to put. Let's put a little physics in there, see kind of what's going on in this in different kinds of ways. Any comments so far? All right. So one of the reasons I put these up is all these links are in the notes. So you can go to the notes, which I've reloaded with the correction of that one example I had. So you can download those. That's it. I put it up before the last test. And you can click on these things and get these various videos that we're looking at. All right, if you want to see it again. There's a whole lot more interesting information in there. All right, then the second one we did last time, not to do too much repeating, is here we have the damped driven oscillator, and the damped oscillator, because we include this term and this one. Now we get a characteristic equation mr squared plus cr plus k equals 0, corresponding to this equation with constant coefficients. And what happens is if these constants m, c, and k are all positive, we said, there's only 3 possible cases you can get to unequal real solutions in which you get C1 e to the R1t plus C2 e to the R2t. We previously discovered for these, but in fact, R1 and R2 are both negative by reason that M, C, and K are all positive. You can show that, it's not hard. So what we get is something that damps out, and we can get that result, or we call that overdamped if we get the 2 real solutions. That what we've done, we have made C, the damping coefficient from the equation, too strong, and the thing just damps, and that's all that happened. Now, if we make C a little less, so that C squared minus 4mk is equal to 0, where m is the mass, k is the spring constant, c is the damping coefficient. Then if R1 equals R2 comes out, then we get this solution, right? C1 e to the R1t plus C2t e to the R1t. And this one turns out to dampen as quickly as possible over all damping coefficients you could pick with the given mass and spring constant. And so we call that critical damping, and that's what returns your car shock after you go over a shock or something, your car to the equilibrium position as quickly as possible, assuming the springs are, looks a lot of spring and so forth. And you got dashpot damper, which isn't necessarily exactly true, but anyway. But if you make your spring, you adjust your spring with a real small damping coefficient, so that C squared minus 4mk is negative, then you get complex conjugate solutions, and you get a damped oscillation, such as is shown in the picture now. And here we did the moving thing last time. I won't replay that. But this is time here, and this is the displacement here. Then the spring goes up and down between, right? You can think of the resulting solution can be written, repeating too much. But since it's been so long since we met, I want to make sure we know our concept, because it plays into everything else we do today. So the solution is C1 e to the R1t plus, I'm sorry, this one. Well, I didn't write out the details above in this part, but it comes out to be C1 e to the alpha t sine beta t plus C2 e to the alpha t cosine beta t, which we said the sine and cosine can be rewritten as a single sine wave. And so it can be rewritten in this form, and you observe that it's a decaying exponential, because it turns out alpha has to be negative due to Cm and K all being positive. And then you get the constant beta out of the characteristic equation. It's got, I think, 2 complex conjugate solutions. Gives you this kind of a solution, a sine wave times a decaying exponential. So it oscillates up and down between e to the ae to the alpha t and minus ae to the alpha t, right? Because sine goes up and down between plus and minus 1, multiplying that. And so you get this kind of a thing where the car goes up and down and gradually settles down in the middle. And that's maybe what you want to save your back in the first place, right? So it's not too big a shock. Okay. Now what we want to do today, I hope I didn't spend too much time on it. Here's the picture again, where it shows critical damping returns to the equilibrium position, right? This is the displacement u here versus time t. Returns to the equilibrium position as quickly as possible for the given m and k. Here's the overdamped case. Here's the underdamped case oscillating up and down between here. Instead with overdamped, you could push it so it goes across once, but then it will just decay back to the middle. And then you can also do this with circuits. We didn't get a chance to mention that before. Let's mention that now. This is in the notes also, but I'll just write it up here. A really nice analogy for electronics engineers is to do this so-called LRC circuit, or sometimes we call it RLC circuit. Let's put them both ways, we said. So we'll say similarly, in LRC circuit, in electronics, you can have, I'll put a switch on here. You don't need the switch, but what you put over here is, let's say I put the inductor down here, is a coil of wire. When I was in junior high school, they used to teach us shop. And we had a quarter where we do electronics, and we build a little circuit ourselves. And then they also had a wood shop and a metal shop and a drafting. And so in fourth quarter, we got some practical life experience, something you don't see so much anymore. We got so theoretical. But one thing we did was we took a little spool, like you put thread on, and we wound wire around it. And what happens, physicists, when you run current through there, it creates a magnetic field, and there's an inductance, they say. But what happens is it affects the charges moving through there because of the interacting magnetic field and so forth. So this is an inductor, and it has a constant associated with it called the inductance, L. And then over here, this symbol going back and forth with the wire is considered a resistor. The idea is if you have a long wire and you put a lot of current through it, it heats up a little, and a little energy is lost to heat. And so this represents losing a little bit of energy through a long wire or something. But that's just a symbol they write, is the wire going back and forth. Well, this is like, think of my little coil going around a spool or something that is an inductor. And then also you can come over here and make two parallel plates. And so you can think of two plates next to each other like this, but they usually draw just like this. And that's a capacitor. You can store charge on one side, and the opposite charge will build up on the other side to balance it. And what happens is current can go across there. So you have, this has a constant ER called the resistance for the resistor, and the capacitor has some capacitance C. And then we can put a switch here just to keep current from flowing until we close the little gate here. And so here's our LRC circuit. And then what is the equation for Q of T, the charge on the capacitor at time T? That's fast. Sometimes I can't write and talk at the same time. Well, it turns out there's a voltage drop across here, and you get zero total impressed voltage. Has to be equal to the sum of the voltage drops across each of these things. And the voltage drop across an inductor here, this coil of wire, is L times D squared. Well, let's write it this way: L di dt, where I is the current in the circuit. So I of t equals the current. The current is the rate at which charge is flowing, so it's actually equal to dq dt. And so L di dt is the voltage drop across the inductor. And then R times I turns out to be the resistance, the voltage drop due to the resistance in the resistor here. And then the voltage drop across the capacitor. And so each of these has a corresponding voltage drop, is 1 over C times Q, the charge in the capacitor. And so you have this equation for the charge and current here, but now I is dq dt, so you rewrite this equivalently. It'll switch sides here as L d squared Q t squared plus R dq dt plus 1 over CQ equals 0. And this is correspondingly the equation for the LRC circuit. The charge on the capacitor as a function of time is a second order differential equation with constant coefficients, LR constants. You know, technically, if you get into the details, circuits have some sort of nonlinear response, and so these aren't exactly constants, but to a good approximation, you can model the behavior of the charge on the capacitor is behaving like that. And then you find the current by taking the derivative of the solution Q if you need that. So look at that. That's exactly what we've been doing, right? If you just replace Q with U, L with M, R with C, and 1 over C with K, it's exactly the same equation. We just called the constants and different letters, and we call this Q instead of U, but it's the same equation. And so actually all those motions we just did correspond exactly to what happens in the LRC circuit with the charge on the capacitor Q. So I'll give you some of those problems where you get those constants and set up this equation for a circuit and get exactly the same kind of behaviors. You can get simple harmonic motion if you just have what's called an LC circuit. You take the resistor out, that corresponds to the undamped mass of the spring. What you get is sinusoidal motion of the charge back and forth, and its derivative, the current, is also therefore sinusoidal back and forth. And you can make, something like you want electrons to swish up and down an antenna and create a electromagnetic wave at a certain frequency. You just tune the frequency here to make the electrons switch up and down and make the antenna the right length. And you can create, radio thing or something with this oscillating LC circuit. But you put the resistor in here, and then you get that corresponds to the damped mass on the spring. And you get those critical damping. You can make the current in the circuit damp out as quickly as possible by making the circuit critically damped, is the idea. All right, so there's all those kinds of things. These are all undriven mass on the spring and circuit without a voltage applied. But now in all these cases, you can do something else. You can apply some sort of external force to the mass of the spring, or you can apply an impressed voltage. By the way, I forgot to say why this equation holds. This is Kirchhoff's law. It's essentially conservation of energy, it turns out. That the sum of the voltage drops around any closed path. Can't ever remember how to spell this. That's probably wrong. There might be 2 H's or something, but Kirchhoff's law says that the sum of the voltage drops around any closed loop has to be equal to 0. They use this analysis. And so here's the voltage drop across the inductor plus the voltage drop across the resistor plus the voltage drop across the capacitor adds up to nothing. There's no impressed voltage. But if you impress a voltage, you put a battery on here or something, then it's equal to the impressed voltage across here. And similarly, the mass of the spring can be pushed with an external force in addition to what you got from the damper and the spring. Now, we also can drive the mass on the spring or the circuit, applying a force or a voltage. That's considered, just for simplicity, the one for the mass on the spring. An external or additional force to the damped mass spring system. An external force, F, whatever, external function can be a function of time, gives what? Well, since all the forces sum, you got md squared u dt squared. The net force has to be equal to minus ku from the taking the force of the spring minus c du dt due to the damper, and then you can add your external force as a function of time. And the idea is that the sum of the forces give you the net force by Newton's laws, md squared udt squared. And so what we get then is this more general equation. The interesting case is when this external force is allowed to be a sinusoidal force. So that's the interesting case, particularly because you might want to drive this thing with an oscillating voltage, right? That's what they used to keep households safe in the early days. If you go back and look, when Edison and those people were trying to bring power to houses, and they were first putting lights out in the park system. It was pretty neat, but you wanted to get it to the, to people's houses, so they didn't have to burn candles all the time, right? Direct current was dangerous. It could start fires and so forth. Well, when they went to alternating current and had an oscillating voltage impressed on here, it was a lot safer. And so that's what motivates a lot of this. So in practice, you often want to put oscillating voltage applied here. So in the special case, that the external force, oh boy, this might have gone off. I guess it's still recording at the moment. Okay, it's hard to tell on this thing. It turns off after. If the external force is some amplitude times a sine wave, so we can put a sine omega 0t plus b cosine omega 0t, something like this, which can also, we recall, since it's the same angular frequency omega 0, you can rewrite it as a single amplitude times sine omega 0t plus phi, a phase shift. So this is actually a sine wave, but we often write it like this, but it's a single oscillating sine wave. What is the interesting case? We now get this more general equation. It's a non-homogeneous linear equation with constant coefficients, right? All these cases we did so far with no impressed voltage or applied external force were homogeneous equation with constant coefficients. Now we've got to sort this out, put everything but the external force on the left. You've got md squared udt squared plus c du dt plus ku equals a sine omega naught t plus b cosine t. And so omega naught is the angular frequency of the driving force. If it's a physical thing, you could think of like pushing your poor little sister on the swing. And all little kids like to tease their little sister because they scream loud, right? Every time she comes back and forth, you might push her intermittently sometimes, and if you push her at a regular frequency, right, then that corresponds to this kind of force and sort of a mass on a spring, with gravity pushing it back. It's sort of like for small oscillations, it's sort of the same problem. It turns out larger oscillations starts to get a little off, but. What happens when you push somebody on a swing like that, and you push them at random times? Sometimes you speed them up, sometimes you slow them down, and you get one motion. But if there was no friction in the swing, and as it went back and forth, and you pushed at just the natural frequency of the swing, your poor little sister go higher and higher until she goes over the top, right? There's a real interesting case where you push it with omega naught at exactly the frequency omega equals square root k over m for the mass on the spring. You can build up bigger and bigger oscillations in the spring, right, by pushing it at the same frequency it naturally wants to move at. And similarly, also in the other case, I should have written that down for the LC circuit. Put this on the side. If you just have, here's a switch if you want. An inductor capacitance, a capacitor with capacitance C and an inductor with inductance L, then the equation becomes L d squared q dt squared plus 1 over CQ equals 0 corresponds to the undamped mass of a spring. And this one then becomes Q double prime plus 1 over LCQ equals 0, has characteristic equation. R squared plus 1 over LC equals 0. And you get a natural frequency at which the charges are going to switch back and forth in the circuit. R equals plus or minus I 1 over square root LC is the solution of this. And you get a motion for the charge going back and forth is a constant times cosine 1 over square root LC. Well, let's call it omega t plus C2 sine omega t, just like you did with the mass on the spring. It's the same thing. The only thing is that now omega is 1 over square root LC. So for the mass in the spring, it does exactly the same motion as long as square root k over m is the same. You double both, it gets the same motion. Now, if you double L and half C, or you make L 1/3 as big, but C 3 times as big, you get exactly the same switching back and forth in the electronics, or the charge is going through there and hits the current also. You get this natural frequency in which the charge flows around 1 over square root LC. So the square root k over m and the mass in the spring and 1 over square root LC tell you the natural frequencies that these things want to move at when you have the undamped case. That's the important point I neglected to mention. All right, so now here's the more general problem for the mass on the spring, and you just change the letters and it's the electronic circuit again. What happens to this one? This has solution what? Well, it's y equals, since it's a non-homogeneous problem, y equals yh t, if you like, plus yp of t, where yp of t is any particular solution, right? And we can get a particular solution, since this is a form that's in the table, right? This is line 3 of our table of undetermined coefficients. So undetermined coefficients applies. And the particular solution can be of different forms, right? Depending on whether the right-hand side here has the form of a particular solution to the homogeneous equation, right? If you look on the table, if this side is a sine wave, then you can look for a sine wave of solution. So if omega naught of the angular frequency of the driving force equals omega, the natural frequency of the system, either square root k over m or 1 over square root LC, depending on which case you're looking at, then what's going to happen? Then the particular solution is not a sine wave. We get a particular solution that's t times a sine wave, t times, if you like, gamma cosine omega naught t, well, or omega t because they're equal, plus delta sine omega t. But if omega naught is not equal to omega, then the table predicts a particular solution that's not a solution of the homogeneous equation, and we get that yp is the same thing without the t. Yp is equal to just a sine wave, cosine omega t plus delta sine omega t. So our table says you get t times a sine wave if you're pushing your sister at the same frequency. That's the natural frequency for the swing to go back and forth. But you just get a sine wave if you push it at any other frequency. And so what's the result in the solution? It's pretty interesting. And I'm sorry, I'm messing up here on this one. For the case, I'm doing this first, sorry. For the case that C equals 0. Very important. No damping, no resistor in the circuit. No damper on the mass in the spring. For this case, you get these two cases. And so this is a form of a particular solution. And this is undamped driven motion. That's the next section here in the chapter, 3.3.3. And what can happen is if you push the mass on the spring at precisely the natural frequency, it builds up a big oscillation in there, and you get an increase of Y particular solution that increases in time and is added to the homogeneous solution, and this is what you get. So the result, again, we're doing the qualitative discussion of these things. We're not doing any new solutions. We're just seeing how they affect physics here. In case one, you get the homogeneous solution as a sine wave because it's the undamped, right? YH of t is the homogeneous problem where you didn't apply force, and with C equals 0, it's the just mass on the spring with no damping, and so that's YH of t. But in case one, the Y particular solution is the same frequency and multiplied by t. So here's a constant times t, I guess I should say. Well, this is a constant times a sine wave times t. And so what you get, that constant is square root of gamma squared plus delta squared. Square root of gamma squared plus delta squared, it turns out, times t. And here would be the line minus square root of gamma squared plus delta squared is the amplitude of that thing there, delta squared times t. And the particular solution is t times a sine wave of the same frequency. And so it looks like that. And when you add these together, pretty soon the homogeneous problem doesn't contribute anything. And you see mostly, again, your portal resistor swings up and down higher and higher until this, this starts to be not a good model anymore. For small oscillations, that's what happens. But your mass on the spring then can swing faster and faster back and forth. They call this resonance. When you push the circuit or the mass at exactly its natural frequency, you can build up huge oscillation and fry your circuit, or extend your spring too far and wreck it or something like that. So that's resonance. And we get this kind of a particular solution, t times that oscillating sine wave. Again, this is with no resistance here, no friction in the, or no damper on the mass on the spring. But in case two, it's very different. Now the particular solution and the homogeneous solution are both sine waves. So here's t versus u again. I should have labeled this here, t and u. And you have a homogeneous solution that goes to one frequency sine wave, a particular solution that goes at some other frequency and amplitude in general. Almost looks like the same frequency, not quite, I guess. Goes at a different frequency. And when you add them together, what you get is the sum of two sine waves, which is kind of a jumble, but it does repeat. Right? If one of these is a multiple of the other, you can get it eventually repeating, let's say. But it's just a sum of two sine waves that might look kind of like a jumble between them. It's hard to say. It's fine. And so you can get this kind of a sum of two sine waves. So there's the two things that can come out of driving at the same at the same or different frequencies, right? Now the interesting case is, well, what if I'm not quite exactly the same frequency, but they're really close? Omega is really close to omega naught, right? Well, wouldn't you expect that there's some sort of continuous change? I mean, it goes from the jumble to jumping off to infinity, and there is, if omega naught is not equal to omega, but is close to being the same, what you do is you start to build up this phenomenon for a while, but then it eventually drops off because really it's the sum of sine waves, right? Because it's case two, because you still get the sum of sine waves. But for a while, the jumble starts to look like it's building up this big oscillation, but then it drops off. Then it starts to build up the big oscillation again, and then it drops off. Your textbook calls this practical resonance. There is a frequency you can drive it at to make these bumps here called beats as large as possible. And so you can think of this as a big sine wave like this. In fact, you can use the trigonometry formula that says the sum of two sine waves can be written as a product, right? And when you get a sum of sine waves with different frequencies, you can always write them as a product. And the product, we can do that if you want here, then gives you a large sine wave multiplied by a faster sine wave, higher frequency sine wave. And you get sort of this interesting sound that for a while the sum of the sine waves has an average frequency that you hear, but then because the amplitude goes up and down in a wave, you hear that going to the frequency here go on and off. It's called the phenomenon of beats. So in case three, you can hear beats. If the frequencies are almost the same but not quite, it tries to build up a big oscillation going to infinity, but it can't quite. And so it starts to get loud, drops off. It starts to get loud, drops off. We can model all three of these things here. Gonna take too long in this. Boy, talking too much today. Here's the phenomenon of beats. This is an MIT demonstration, better than I could do in the classroom. They're going to model something else here. They're going to show how these are two tuning forks stuck in a box. So you strike the tuning fork, it makes an almost sinusoidal sound wave go through the room. Pressure variations waves go through the room and if these two tuning forks are exactly the same frequency, you can transmit sound waves from this tuning fork into this. This is how a radio antenna. If you get two antennas that oscillate at the same actual frequency, you can transmit from one antenna to the other. We're going to put a clamp on the line. And that'll make it oscillate at a little different frequency. And what you find is the sound waves from this one box is just an amplifier. Don't transmit to this one anymore. And so this shows you won't pick up other frequencies in your radio car. That's a side comment, just to learn a little about waves. And now, if you keep those at close frequencies but not equal, and you strike them both, now you've got two almost equal frequencies. And here's what happens. Each one is making a constant sound, but between them, you've got going on and off. Average frequency of the two is the note that you hear, but it appears to go off on and off due to the phenomenon of beats. All right, so let me get rid of that one. It's going to play something for me. Don't want to see a commercial. Escape, that's what I want. Save me. All right, so that's kind of a fun demonstration of what happens if you have the driving frequency almost at the natural frequency of the tuning fork. All right, this is a tuning fork for musical instruments. It's got the two tines up here, and when you strike it with the hammer here, the tines swing back and forth and put pressure variations in the ambient through the ambient pressure in the room, and your ear picks those up, and here's the sound is the idea. And it's almost sinusoidal for a nice tuning fork because the metal swings back and forth nicely like that. So anyway, then the right length and material, you can make it just the right notes. Anyway.
What's the formula for case 3, if K is close?
If omega naught, the frequency at which you're driving the system, is almost equal to omega, which is square root K over M for the one, or 1 over square root LC for the other, the frequency at which it naturally wants to oscillate. So think if you push sister almost at the same frequency the swing wants to swing at, it'll go bigger and bigger for a while, but then eventually you'll be pushing at the wrong time and it'll damp back down. Then it'll build back up and damp back down. And you get these beats, there it is. Yeah, so when they're almost equal, but not quite. Helps if they're almost the same amplitude also, but you'll get some beats regardless. Okay, I'm getting my mail mixed up here. I don't need that. Now here's the example of resonance, right? What happens in resonance is this, right? The particular solution goes like this and blows off to infinity. In practice, that doesn't happen because there is a little resistance in the system, right? Eventually, the heat builds up and the circuit fries or something instead of, but here in the model, your current builds up to infinity. And so oscillating back and forth and the charge, when you drive the circuit, it's just the same frequency. It naturally wants to switch the charges back and forth at. This applies to bridges, for instance. This is the Tacoma Narrows Bridge built in the state of Washington in 1940, I think it was, before they knew about the effects of building up a natural frequency. This is why when you have your soldiers march across bridges, they put them out of step. They don't want to build up a natural oscillation in the bridge. If you oscillate at the right thing, then the bridge starts to bounce. And so this is an example of resonance in a bridge that they built. This is a real bridge. They only had like 40 miles per hour wind. We get those winds all the time here. And it was practically new. And this is what happened to the poor bridge. It's very. Yeah. Okay, so there's that one. They did rebuild it actually. You go out there and see it today. I think they've got actually a second structure, if I remember right. Look up the Tacoma Narrows Bridge on Wikipedia, you get a big write-up on it. Tell you all about it. But the idea is that if you take something that behaves like a mass on a spring and shake it at just the right frequency, you can build up big oscillators. All right, and then I wanted to make the comment that all this assumes a massless spring, right? We had a mass of the force from the spring, but if the spring has mass, interesting things happen too. This is just for fun. This is not for test or anything. But you take a slinky, right, where there's no mass attached at the bottom, and suppose I drop the top part of the slinky, it's all pulled out here. It's just a spring, a compressive spring. What happens if I let go of the top? Anybody know what happens when you take this spring where you have the bottom, the spring having mass, because there's no mass at the bottom of it? Here's a fascinating thing in slow motion. I'll just show you just for fun. So sometimes you have to take into account the mass of the spring too, and we won't do that here. Here's what happens. It's fascinating. I just wanted you to see it. Anyway, that's all. Anyway, so you can click on all those things in the notes and see all these videos. But that's to get on, get some of the physics of this. Now, we need to do an example here today. Where'd my, oh, I clicked on the thing today. I'll just have to bring it back up again here then, hold on. There we go. Okay, so there's the links you can click on. Let's now do the undamped, I'm sorry, the damped driven motion. Sum of sine waves from driving, let's see. Let's do this case right here. All right. Here's another example. The final example here is suppose I drive it not near its natural frequency, so I'm just adding 2 sine waves. Here's an example of what you get. And again, it's just doing mathematics we've already done, but I wanted to actually do an example. Suppose I have a mass on a spring, subject to damping and driving. And suppose it's a unit mass equals 1. This is the undamped driven.
Are we on the damp driven motion or? On
Yeah, I'm trying to do the damped driven motion. It's the next part, sorry. There we go. There we go. 1 kilogram mass. So M equals 1. Hangs near the end of the spring with Hooke's law constant K equals 5 newtons per meter. Is attached to a dashpot damper with C equals 2 newton seconds per meter. Driven by a force F of T, so you apply an external force, push it with your hand or a little rocket motor or something. 8 minus 8 cosine 5t minus 4 5 sine t. I picked those numbers so so it's essentially sinusoidal driving. These add to a single sine wave. The characteristic equation, we first want to solve the homogeneous problem. Let's say this is an equation 1 times d squared u dt squared, where u is the position of the mass, plus c is, I'll write down, c equals what? 2. Plus 2 du dt, plus k is the spring constant 5u equals the force on the right-hand side, 8 cosine 5t minus 4 sine 5t, right? So that's your equation. How do you solve this equation? By what we did before, right? We simply break it up into two pieces. We say, one, we want to solve the associated homogeneous problem, right? So we solve one, we look at u double prime plus 2u prime plus 5u equals 0. And we solve for the homogeneous solution. I'm calling it H. And this got a characteristic equation, r squared plus 2r plus 5 equals 0. Or I solve that by the quadratic formula, I get r equals minus 1 plus or minus 2I by solving that quadratic formula. And so I find out the homogeneous problem, motion of the mass if I weren't driving it, would be C1 e to the minus t cosine 2t, right? Alpha t cosine beta t plus C2 e to the minus t sine beta t. That would be the solution if I weren't driving. But now I have to take into account there's a particular solution added on because I'm driving it. And I'll say UP comes from, by the table. Well, if the driving force is a sine wave, it has the form by the table of undetermined coefficients. Write that down here. Also a sine wave, right? And we don't need to multiply by t because the sine and cosine are solution of the homogeneous problem. It's an exponential times a cosine and sine is an independent solution, right? So it's a yp equals gamma cosine. We're driving it at a frequency of 5t, cosine 5t, plus delta sine 5t. So there will be a solution to this form. Plug it into the differential equation, the original one, original dE determines the coefficients, and I'll just say what they are because we're out of time. We find out what gamma and delta are, and they come out to be, all right, let me finish this one real quick if I may, so I don't leave it in the middle. C1 is 3/5 and C2 is 3/10. So it's, oh no, I'm sorry, that's the initial conditions. Yeah, one of them is 2/5 and the other is 0, and you get yp equals gamma is 2/5. The way I've written it here, I may use different letters on in the notes, and delta equals 0 is what it turns out. And so the particular solution is 2/5 cosine 5t. And now what's the general solution to the whole problem? The general solution to the mass in the spring with this setup is the sum of those two. Y equals C1 e to the minus t cosine 2t plus C2 e to the minus t sine 2t plus what you got down there, 2/5 cosine 5t. And this last case now is for damped and driven motion. What happens? You get a homogeneous solution that's a sine, that's a decaying sine wave, right? This is the damped oscillator without driving here. This is the homogeneous solution, and so this one looks like this. It oscillates between two decaying exponentials, but this one, the particular solution, that's UP. This is UH, is a steady sine wave, so it looks something like that with amplitude 2/5. Right? And what happens when you sum these, when you have a damped and driven system, is that you get this transient solution, transient part of the solution that damps out. That's the homogeneous solution, and you get this steady state sine wave. And so when you have a damped and driven system, what you get is the sum of the two of these, and together they look like initially, maybe this one affects it and then they're kind of a jumble, but eventually it settles down into the steady state because this one damps out. So the sum, U equals UH plus UP, which is the solution to your problem, right, is U versus T. is actually something that settles into a steady state. This is important with the circuit, it tells you in the long run, it's just oscillating like this, because the initial thing gaps out. Now, what are C1 and C2? This is the general solution. These are determined by the initial conditions. If you tell me the initial charge on the capacitor and the initial current in the circuit, that will determine C1 and C2. Or if you tell me the initial position and velocity of the mass in the spring, that will determine C1 and C2. So this is the behavior in any case, but where it starts and how fast it's moving determines C1 and C2 in the exact solution. Okay, so I'm sorry I'm slightly over. Let me put homework on here somewhere. Take a look at these and see if you can do these interesting cases of what happens. What are the qualities of solutions in all those cases? Resonance and beats and transient plus steady state terms and sum of two sine wave kind of stuff. 3.3.3 out of the notes. 1 to 3. And 3.3.4. 1 and 2, and now that'll finish all these things on applications, and we can move on to something new tomorrow. So thank you for your patience. Postman lets you go a little early tomorrow.
Professor,
Yeah,
covered undamped driven motion today, and I didn't notice.
that damped and driven is the last example. If you have a damper so that you've got a non-zero coefficient of U prime.
I mean for like section 3.3.3, did we cover undamped?
Yeah, that was the other cases, the beats, the resonance, and the sum of sine waves was the undamped. And then the damped is just this, you get transient and steady state. Yeah, this is 3.3. Okay, thank you so much for coming in today.
Also, can I see what my grade is for this class?
Let me get this off here real quick.
Oh, did you get that?
Yeah.